Hello, good morning. How are you? I hope you have slept well. So today we will start a new part of the module. First of all, let me know if you can hear me, as always, with thumbs up in the announcement I'm doing. Okay, thank you so much. So as I was mentioning, today we will start a new part of this module. So we have seen in the first part instructions, compute the language of the computer, and now we are going to see arithmetic for computers. First of all, I would like to mention I had some feedback and someone told me that if I could slow down, so I will try to slow down during this lecture. So let me know at the end if this rhythm, if this pace is better or not, or if it's too slow. And as always, remember that you can give me feedback directly, anonymously, and we have also our course rep and module reps. So if you want to give me feedback regarding how to improve the lecture, so you are more than welcome. We also can arrange, if you want, a review lecture or some kind of office hours. So just let me know, and I'm happy to help. Okay, having said that, let's come back to the module. So in the previous lectures, in the previous part, we have seen how integers can be represented in binary form, right? And but what happens with other kinds of numbers that also that we also find in when doing operations, for instance, fractions or other real numbers. And also interestingly will be what happens if an operation, an add or a subtract, creates a number bigger than can be represented. And also another question will be how does the hardware actually multiply or divide numbers? So those kind of questions are the ones we are going to try to address in this part of the module. Okay. As always, remember that part of the material is extracted from the book. So let's start then with the outline of this particular lecture. So we will see binary addition, binary subtraction. We will see something called overflow, and finally we will see what is the arithmetic logic unit. Let's start then with the binary addition. So, for instance, here for the binary addition is similar to the decimal one. We just add bits, add digits bit by bit from right to left. There is something called carries, which is similar to decimal, which are passed to the next digit to the left. Let's see some examples here. For instance, if I want to add the binary digit 0 to the binary digit 0, just 0 plus 0, we have 0, and then what we have in red is what we call carry. In this case, the carry 0, we don't have a carry here. So imagine now we are going to add 0 plus 1. Again, we have the result is 1 and no carry. 1 plus 0 is the same result. And interestingly here is what happens when we add 1 plus 1. So the result is 0, but then we have here a carry. So we will need 2 bits to represent the output of this operation. Otherwise, if we just have 1 bit 0, the result will not be correct. Okay. So let's see a more complex example. For instance, let's say we want to add those two binary numbers. You have the conversion in decimal here, okay? So this is the binary number, and this is in the right part we see the equivalent in in decimal. So we will perform the addition from right to left. So first of all, we add the rightmost 2 bits. Okay, so 1 plus 0 is 1. The carry is 0. Okay, so now we have 0 plus 1 plus 1. The result is 0. And here we have a carry, we have 1. So we have 1 plus 1, which is 0, plus 1, which is 1. And we have a carry from this, which is 1. Okay? And then we have 1 plus 0, which is 1. And the final carry is 0. Okay, I think this is simple to follow. And what we can do to check if we have done this correctly is just check the result with the decimal operation. In this case, 7 plus 6 is 13. So if we convert this binary number 1, 1, 0, 1 to decimal, we get the value 13. And with this, we know that this operation is correct. Okay. So let's see now the subtraction. What are we going to do the subtraction? So if we want to subtract, for instance, 6 from 7, what we are going to do is doing an addition, but subtracting the negation of the second operand. Okay. We have seen in previous lectures in the networks part that for negating an integer, what we can use is something called the choose complement, right? Which basically consists on inverting all the digits and adding one. We are going to see some examples of this. For instance, if I have the positive integer 2, which is the value in decimal in binary will be 0, 0, 1, 0. If I want to negate this 2, if I want minus 2, then I will invert all the bits. So I will invert 0, which is 1. I will invert 1, which comes to 0. I will invert 0, which comes to 1. And I will invert 0, which comes to 1. Okay. So the inverted values of 0, 0, 1, 0 is 1, 1, 0, 1. Okay. And then I just add an additional 1. And with this, we have the choose complement of the original 2, which is equivalent to minus 2. Okay. This is the way we are using to negate one number in order to subtract it. So, and this method is called the choose complement that you have seen in the networks part. For instance, some useful values. The value of 0 is represented just with 2 zeros. In this case, notice that we are using only 4 bits. Okay. Then if we want to represent the value minus 1, it will be all ones, which actually is and then if we want to represent the most negative number using 4 bits, it's minus 8, which is this one here indicates that it's a negative value. And the most positive value will be plus 7. So this 0 here indicates that it's a positive value. And then let me show you this graphically. Okay, so the most positive value using this notation will be with 4 bits will be plus 7, as I have mentioned here. Okay, so if we go up, we have positive numbers. Here is the 0 number. And if we go down, we have the negative numbers. Everything starting with 1 is negative. Everything started with 0 is positive. Okay, makes sense? So I have mentioned the operation to negate one number with the choose complement is very simple, and you can see this example here. We are just inverting the digits from the positive number and adding one. And by doing this operation, we get the negative number. Okay. As I have mentioned, this is for using 4 bits. If we would like to use more bits, it will be something equivalent with more bits, and the most negative number will be higher, the most positive number will be higher also. Okay. So let's see an example of subtraction. So imagine that now I want to subtract 7. I want to subtract 6 from 7. Okay. So for representing the 7, it's okay. We know how to do this. And what about representing the 6? So for representing the 6, what we need to do is I have the number 6, which is with 4 bits is let me check. The number 6 is 0, 1, 1, 0. Then if we invert those bits, we get so 0, 1, 1, 0. We get sorry. Let me check. Well, if we go to the previous slide, so we know that 6 is 0, 1, 1, 0. Okay. If we invert those bytes, we get 1, 0, 0, 1. And if we add 1, we get 1, 0, 1, 0. Okay, makes sense? I think it's clear, but just in case. Okay, number 6 is 0, 1, 1, 0. Then if I invert those bits, I get 1, 0, 0, 1. And if I add 1 to this number, I get 0, 1, 0, 1, 0. Okay, so this will be plus 6. This will be inverting numbers. And this will be adding 1 to the previous. Okay. And this is what we call choose complement. So this value here is what we have actually placed here in order to subtract those two values. And then we do the same as with the addition. So 1 plus 0 is 1, and then the carry is 0, 1 plus 1, 0, and the carry is 1, 1 plus 1, okay, 0, makes sense? And then we have this number. And if we check the result with the decimal operation, 7 minus 6 is 1, which is actually what we have here. Okay, makes sense? So now I propose you to do a more complicated exercise, okay? I propose that you do this operation. So I have a form here, and then I give you a couple of minutes to subtract 122 to 185. Notice that those are in decimal. I want you to convert those to binary and then subtract them using 8 bits in this case. The previous example we were using 4 bits, so now we are going to use 8 bits. So I give you a couple of minutes. Okay, time is over. So let's check the answers. I have not very much answers. We have 17 answers. I'm going to show you. We are going to see the solutions now. Okay, most of you got the correct. It seems that most of you get the. Okay, someone is telling me that the form removes the capital zero. So yeah, that's a problem. So yeah, so it's not working very well the form because it's removing the zeros. Okay, so no worries. So at least you have tried it. So now we are going to try to understand how to perform this operation. Okay. So what we have done here is, so we have converted 125 to binary, then we have converted 122 to binary, we have inverted the values and added 1, and with that we have the negative value of 122, and then we have added those two values, 185 minus 122. Okay, and this is what we have seen previously. 1 plus 0 is 1, 0 plus 1, 1, 1, 1. All of those are 1. Okay, 0, 1, and yeah, I think it's clear from what we have seen before and what we have done now. Don't worry about the form. I know that it is not checking the result well, but yeah, I will try to fix it for the next form that we are going to do now. Okay, so I'm going to propose now a similar exercise. Okay, but now instead of subtracting, what we are going to do with the same numbers, we are going to add them. Okay, we are going to add 185 plus 122. So please, I give you some time again to do this operation, and I will try to fix the form and share the form again through the chat. And hopefully, once you have finished, the form is ready and fixed, and you can put your value there. Okay, so the time starts now. You have 2 minutes to perform this operation. The new form is there for exercise 2. Okay, so the time is over. I got a lot of answers here. 38 answers. I don't know if this time it has worked properly. So this is the answer I mark as correct, but we will see now it has some some things we will need to check. So what I have done here is again 185 in binary, then we have 122 in binary, and then just adding them as we have done before. And with this, we have this number. The problem is that if we check it with the decimal value, so the correct result is this one, not the one I get. So this is what I wanted to highlight here. So if we use 8 bits, as I was requesting in the exercise, we cannot represent correctly this value. So using 8 bits, the 8 bits, the result for this operation will be that one. But it's not correct because we cannot represent the output of this operation with only 8 bits. We need 9 bits. Okay? So this is precisely what we call overflow. When this happens, that we cannot represent a value with the bits we have, we call this overflow. So let me check if I see any answer, any question here before I continue. Okay, let me check. So someone is asking, why cannot you add them as decimal numbers and convert to binary afterward? You could do that obviously, but what I want to show you here is how those binary operations are done, because later when we see how the hardware works, the hardware will try to emulate what we are seeing now. Okay, so I'm not showing you how to do this for using this way of subtracting and adding binaries in the future. We are seeing this because we want to understand how the machine is working, so how the underlying hardware is working, and what we are seeing now is similar to what the hardware is going to do. Okay, hope that helps. And then let me check if I see any other question. Someone is asking also, can we do the binary subtraction directly instead of transforming the problem to a binary addition? In this module, we have decided to do this in order to simplify later the hardware and everything. And this is our decision. So would it be possible to follow other criteria? Yes, but in this case we are doing this, as mentioned, because later when we show how the hardware works, it will do something similar. Okay, so let's continue then with the overflow. So as I have mentioned, overflow is when a result cannot be represented with the available hardware. In this case, we have seen that in the previous example, we needed 9 bits, but we only have 8 bits. Okay, so if we do all the operations we have seen, the only problem we need is when I add 1 plus 1. So it's only there where I need 2 bits to represent this result. Okay. So how do we manage overflow in LegVI, in assembly language LegVI? So for that, we have the flags. Remember, yesterday we also mentioned those condition codes or flags. So, and if you remember, we also commented that we have 4 condition codes. One was negative, one was 0, And the one we are focusing today is the overflow, which is actually this thing that we are mentioning. So if we use any of those operations with the condition flags on, with the S, what will happen is that if we try to add two numbers and we get an overflow, this condition code, the overflow, will be set. Okay? And we also have another condition code that we can understand now, which is the carry. Okay, now you understand when this value will be set. It will be when I add two numbers and I have the carry on. Okay. If we come back to what we saw in past lectures, we can now understand the rest of the branch. So remember that we have used all this branch, but for conditionally jumping to a level in our LegBI code, and now we can understand this. So with branch equal, we mentioned that if the condition code 0 was set, it means that the numbers were equal, and if it was not set, it means that the numbers were not equal. So now we can understand also what is happening for doing the other branches. Okay, how we manage the B, the overflow, and the C, the carry, in order to get the other conditions less than, less or equal, greater than, or greater or equal. Okay, so now we have seen all the four codes, and now we are able to understand how those branch instructions actually work. So let me focus now on this overflow code. For instance, I have this conditional branch b.bs. So this will branch on overflow set. This will mean that if my operation, the result of my operation resulted in an overflow, this condition flag will be set and the branch will be performed. So it will jump to a specific part of the code. And this is if the condition code is 0. Okay, I have added here another examples, branch on minus and branch on plus, which means it's using the condition code negative. Okay, similarly to the overflow one. So let's see an example using those condition codes. So here I have this LegBA code. So now what I propose you is that you analyze this code, and the question here is, will it work properly? So I'm going to give you some time, okay? And let me know at the end if it works or not. Okay, so the time is over. So I have put in the chat two statements. One is yes, it works, and the other is no, it doesn't work. So if you could thumb up the one you think is right. I see some of you. Okay, so most of you are right. So most of you think that it doesn't work. And the reason is, as you probably have guessed, because we are not using the correct instructions, okay? So we need to use the correct instructions to set the flags. If we don't use the add is and the sub is, flags will not be set and this code will not work, okay? So I show you the difference. This was the initial code and it's not working because the add I instruction here and the sub I instruction here doesn't have the set flags, okay? So now that we have the set flags on, let's analyze the code. So the first instruction is clear. We are just adding 0 plus 0 and putting this value in register 9. And then what we are doing next is, while there is no overflow, we increment the value of register 9 with 1. Okay, so this loop will happen again and again and again until we reach the maximum positive value for register 9 after adding 1, 1, and 1. Okay, makes sense? And then at some point, this will not happen. So we will have overflow. And what will happen is that this instruction will not branch, but this instruction will branch because the overflow flag will be set and we will branch to a part of the code in which we have the overflow. And what we do is just subtracting 1 to the register 9, which was the last increment, which was the one which produced the overflow. Okay, makes sense? So basically here we are undoing the last increment in order to have the value right. So now my answer is, if you analyze the following code, which is also using something similar, but we have here some other kind of instruction. So if we analyze this code, can you tell me what will be the value of register 10 in hexadecimal at the end? Okay, so I have another form for this. You have also the same code in the form. This is a more complicated one. So right now, we are going to have 4 minutes for this. Okay, starting now. So let me know if you can guess what will be the value of register 10 at the end of this code. Okay, the time is over. Let me check the results. So those are the results we got. Okay, and now I'm going to try to explain what is the actual result. Okay, so let's analyze the code line by line. So first of all, we are using this mob 0 instruction that we saw yesterday, which is just modifying the first quarter of the register with this hexadecimal value we have here. Okay, just putting this in the first quarter. Then we are using the mob, but keeping the rest of the bits. Okay, so in this case we are modifying the second quarter, which is this one, and we are putting all f there. And then we are doing the same with the third and the fourth quarter of the register. In the final one, instead of all being f, we are adding this 7fff. And now the loops start. Okay, at this point, the value of register 10 is in hexadecimal this and in decimal this. And now what we are doing is we are adding, as before, in a loop, adding 1 to 10 to register 10, and again, while there is no overflow, this will loop, and once we have overflow, we will jump to a similar part as before in order to undo the last increment. Okay, so in this case, the value of register 10 will be the maximum value, the maximum positive number with 64 bits. So the overflow will happen when when we have this number. So when we increase, when we pass the most positive number using 64 bits. So when we pass this number 7fff all f's, when we add 1 to this number, we will get 1 and all zeros, and this number this result is not correct because the number is negative, and if we are adding 1, we can only get positive numbers. So when we get this number, we will have the overflow, and it's then when we go to the overflow part of the code and just subtract 1. Okay, makes sense? Okay. So now what we are going to see is which component of the computer actually performs those operations. So we have seen that we have this computer architecture which we refer to as von Neumann, and what we use for performing those operations is what we call arithmetic logic unit. So this is the part of the computer which performs add and subtract and or operations. Okay, so if we go back to our architecture, remember we have the memory, we have the central processor, we have the control unit, the data path, and inside the data path we have the registers that we have already seen, and now we have this arithmetic logic unit, which is actually the hardware which performs the add, the subtract, the AND, the OR operations. Okay, so graphically we represent it with this figure here. So this means, for instance, if we have an arithmetic logic unit of 1 bit, we will have two inputs, so 1 bit and 1 bit, 2 inputs bits, and here we will do an operation. So imagine we want to add 0 plus 0. Here we will do the add, and the output will be 1 bit. This is just how to represent graphically this arithmetic logic unit. Okay, so we have seen today how to add numbers in binary, how to subtract numbers in binary. We have seen how to manage when we don't have enough space for storing the result in the hardware we have. And we have also seen which part of the computer is capable, is the one which performs these operations. And now in the next lecture we will see multiplication and division, but now I want to answer some questions. First of all, let me correct, someone has mentioned, and it's right, there was an error. Okay, so listen now, there was an error in this slide. So in this slide here, the operation, I have now fixed it. So before this operation we didn't have a carry, but we have a carry here. Okay, I think this is what someone was pointing out. So this was a mistake. Okay, in the previous slides I have shown you there was not carry here, but this is the correct mistake. This is the correct slide. I have fixed it, so it will have a carry also, and then it will have a carry here, and it makes sense because. So what happens here? That in this case we have an overflow, right? But why we have an overflow? Because we have a 1 here, but the result is the same. The result is okay. So we have a 1 here, but in this case, if we check our slides, so with 1 1 at the beginning, it should be a negative number. So what is happening here? So we are subtracting 6 from 7, which is 1. So we supposedly with 4 bits, if we went to this slide, we are capable to represent this. So 7 minus 6 is 1. Yeah, so I actually don't see. So 1 plus 0 is 1, carry 0, 1 plus 1 is 0, carry 1, 1 plus 1, 0 again, carry 1, 1 plus 1, 0 again, carry 1. Okay, this is the correct result. In this case, the decimal operation also matches, but there is an overflow here. Okay, but I think that this is what someone was pointing out in the questions. Hopefully that is clear now. If not, let me know it again. And now let me check if I see some questions. Okay, someone is asking if I can go to over the last example, which I guess is this one. Okay, the value of 10. So here, I think these all 4 instructions are clear because the one we are modifying is the red thing. So with this operation, we are just putting this at the end of this the first bits of the register. Then we are putting this here, this here, and this in here. Someone is asking why this is 7, because I have decided to do so. Okay, for doing the exercise more complex. So it was my decision. Having here a 7 and not an F is just my decision. It's not for anything special. It's just for making the exercise more complex. And now, so here we have this value in register 10, and what we are doing is incrementing 1 by 1 by 1 by 1 until we have the overflow. And once we have the overflow, we go to this part of the code and we subtract 1, and by doing this, we undo the overflow. Okay. So I see more questions coming. I will try to answer those questions here in the chat. And again, if something is still not clear, you know that we have the ticket system you know that we have, you can also contact me. And as always, as I have mentioned at the beginning of the lecture, there is a module rep. There are several module reps. So if you want, we organize a review section or something, or an office hours or whatever. Just let me know. I'm happy to help always, and happy to explain if you need. Okay. Thank you so much. Have a nice rest of the day. I will publish at 1 lab. The lab 1 for this week. Remember that the solutions for that lab are always released on Fridays at 1. Someone is also asking where I find the solutions. So I think this is clear, but just in case. So if you go to the lab 0, for instance, you see that you see that here you have the initial lab, then the solutions, and then if you go to the videos, there is a video explaining the solution here. I think that's clear because I saw that you have seen the videos, but there is a link explaining this lab also here. Okay. So hope that helps. Thank you very much. Have a nice day, rest of the day, and see you next week. Thank you. Bye bye. See you.